Okay, so we're gonna finally start statistics. This course is not a statistics course. So what we're going to do is to give a shallow introduction to statistics, okay? For those of you who are already taken statistics or who is into doing statistics right now, this will be very, very simple, okay? For those who never saw statistics, I hope it's fun, right? And statistics is fun. Okay, so what we can do with these random variables, we can do what we call statistics. What is statistics? Well, statistics is an area of mathematics that studies random variables, okay? So we study random variables, and a statistic is a measure of this random variable. Okay, so let me give you a definition. So statistic analyzes and interprets the data. Okay, I think this is written wrong. I have to change that. I didn't change yet. Analyzes and interprets data. And the statistic, what we call a statistic, right? So in statistics, it's an area of mathematics that studies this data through several statistics. And a statistic is a measure of that random variable of your experiment, and it will give you a property of that random variable. Okay, so the first statistic that we start studying is called the mean. Okay, so this is the first statistic, is a measure of a random variable, and it will translate it into a property. Okay, and it's called the mean. The mean, or the expected value. Sometimes you can hear as an average as well, as average. But expected value is it's the most, I think it's the right name to give it, okay? So so I'm going to teach you, first of all, how to calculate this measure, this score. So a statistic is a measure or a score. This mean statistic, or the expected value statistic, is a number that you can calculate, and it will give you a score. And then after that, I'll tell you what it means, okay? So how do we calculate a statistic of the mean? I'm sorry, let me put this back. Let me put this back. Okay. All right. So what is the definition? Well, the definition is given by this formula, this operation that you need to do to calculate the expected value. Okay. Okay, so this is the formula. You can also see this formula not condensed, because this is a condensed way of showing this calculation. This symbol here is a sum. So you will take the little x times the probability of your random variable being that little x, and you will do that up until you got all your x's. So from the first x to the nth x, okay? Now, this can look a little bit cryptic, but we know who is little x, right? If you take a look at the PDF, little x is the left-hand side of the PDF, and P of capital X equal to x is the right-hand side of the PDF, okay? So sometimes you will see this formula opened up like this, like, oh, for x1 times the probability of that happening, or that your capital X is equal to little x, so your variable is little to x is equal to little x1, plus the probability plus the second outcome of your experiment times x is equal to little x2, and up until xn is equal to that. Okay, so sometimes you will see this formula as well as the definition of the average. So again, let's say that you're doing an experiment, okay, and your variable can assume values, I don't know, 0, 1, and 4, and the probability of that happening, the probability of x being 0 is 1/6, the probability of x being 1 is 1/3, the probability of x being 4 is 1/2, okay? So what this formula is telling us is, well, take the little x, take the value that your take the value that your outcome, the outcome of your experiment can assume, and multiply by the probability of that being, and sum up all the possibilities, okay? So if you think about this PDF, this example PDF, the expected value, the statistics of the expected value of this PDF is this. x1 is 0 times the probability of being 0, this is 1.6, this is 1/6, plus what's the second value that your variable can have? Well, your variable can have 1 times 1/3, which is the probability, okay? Plus the last one is 4 times 1/2, okay? And that's the statistic. So if you carry on this calculation, 0 times 1/6 is 0. 1/3 plus 2, this is 2 plus 1/3. It could be written as 2.333. Okay? So this is the mean, this is the average. So at the end of the day, what you have to do to calculate the expected value is multiply x by the number by the probability of that happening, right? For all the rows, and then just sum up that that number, okay? Some people like to do like this, x times p of x equal to x. So it's representing the multiplications. So it's 0 times 1/6, 1 times 1/3, 4 times 1/2, right? And then they just come up and sum this column. So sum the column. Okay? That's how you calculate the expected value. Okay. Now, what does the mean tells us? Okay? Well, let's draw this PDF, this probability density function, as an histogram. So we're going to do, well, it can assume 0, it can assume 1, and it can assume 4. And you will have different boxes. Okay. I'm doing a mock histogram first, and then I'm going to put the areas. So this one is 1/6, then a 1/3, then 1/2. Well, it's not in scale, okay, but it's the area of this has to be 1/6, the area of this has to be 1/3, the area of this has to be 1/2. Okay. So let's find the mean value. It's 2.33333. So let's find it. It's actually here. It's 2.3333. So what does this number mean? If you trace a line here, right, in your histogram, you will see that this value is kind of pending. It's dislocated towards number 4. Okay, meaning, what's the meaning of the mean? Well, the mean is a weight on your likelihood. Okay, this is more, it's closer to 4 than is it a 0, meaning that you have more likelihood, you have more chances of having an outcome of your experiment taking on number 4 than on number 0. Okay, so it's 4 and 1, they are kind of pushing the mean to the right-hand side of this graph. You can think of the mean being as a scale that is kind of weighting your probability. So if you have a scale, think about a balance, right? So think about a scale like this, where you have a balance. This scale, this figure here, the number 4 is more heavier to the right-hand side. So you're kind of pushing the line more towards 4. So that we can have this concept clear, let's think about a fair coin. This is a fair coin. So if you're tossing a fair coin, what's the histogram of that? Well, that can be 0, that can be 1. And if it is a fair coin, you will have this area as a half, this area as a half, okay? What's the mean? Well, let's calculate the mean in this case. So the mean is, you can do it through the PDF, or you can do it directly from the graph, okay? So the PDF is this: you can assume 0 and 1, and the probabilities are a half for each one, okay? What is the mean? Well, take the value, the expected value will be the value that your variable can take on the first row times its probability, plus the second value times its probability, right? And if you calculate that, this is 0 plus a half, this is a half. Okay, so let's find a half in this graph. A half is exactly here. So if you think about the mean as being a scale, both 0 and 1 has both the same chances. So the mean is actually in the middle. It's in equilibrium. Okay. Now, what if I do an unfair coin? What if I toss an unfair coin? Okay, so this is the first case. It's the case of our example. This one here is the fair coin example. Let me give myself some space. Okay. And now we're going to work an example where we have an unfair coin. Okay. So let's do the histogram of an unfair coin, 0 to 1. And I'm going to do it, I'm going to do it like this. 0 and 1. So I don't know, maybe this is 1, this is 5, 6, and this is 1, 6. It's not in scale, okay? This, in theory, this box here should be 5 times taller. Well, let me try to do it in scale. Just wait a second. This is 5 times. Well, this one's like this. Okay, so this area is 1, it's 5, 6. This area is 1, 6. Okay. All right, let's calculate the expected value of this. And I'm not even going to do the PDF. I don't need to, because I know how to read the histograms. The histogram is just the PDF, but it's graphic. So what are the values that my x can assume? Well, it can be heads and can be tails, or tails or heads, tails and heads, 0 or 1. So it's the value of the variable times the probability, which is the area, it's 1/6, plus 1, it's the value of your experiment, it can assume heads or 1, times the probability of that being, which is the area of that box, is 5/6. So if you calculate this, this will be 5/6. Okay. So if you find this value of 5/6, which is I think it's 0.8 or something. This is 0.833. Yeah, 8.333. If you find this variable here, it's here, right? Again, it's an unfair coin. The mean is telling me, so this is 0.833. The mean is telling me that I am more likely to be on the right-hand side of the graph. My variable is more likely to be 1 than it's to be 0. So the mean is kind of, the expected value is kind of a this scale that weights your probability, that weights your likelihood. Okay? All right. So I just want to discuss something very briefly that came up during the sections. Somebody asked, what's the difference between the expected value with the average we learn in high school? Okay. So let me give you an example. In high school, we learned that think about a variable that can and this variable can assume 0, 1, and let me do another example. 1, 2, and 3. Okay. So this, and if you are asked to calculate the average in high school, the average, you will do, well, this is 1 plus 2 plus 3 times 3. This is what we learned. Okay, so you take the sum of the values and you just average. Okay, so let's say that this is a score on a test. A friend had 1, a friend had 2, a friend had 3. What's the average? That's 1 plus 2 plus 3. This is what we learned. Okay? This is 8/3. Okay. Oh, no, not 8/3. Sorry, 7/3. 6/3. Oh my goodness. This is Jesus. 6/3. This is 2. Okay. Just thinking about ahead. Okay. So now let's think about this, how this relates to expected value. Well, this is actually a particular case of the expected value. Okay. Why is that? Well, because if you do the calculation of this way, you're actually doing this. You have a random variable, I don't know, a score on a test that can have values 1, 2, and 3, right? The 3 friends had these values. And if you think about this as an equiprobable sample space, meaning that taking number 1 is not more probable than taking number 3 or number 2, what's the probability of 1, 2, and 3 happening? Well, it's 1/3, okay? If you think about equiprobable sample spaces, everyone has to be equal, and you have to sum up to 1. Like the PDF has to sum up to 1. So it has to be 1/3, 1/3, 1/3, okay? Because 3 times 1/3 is 3, okay? Now, if you apply the expected value here, okay, you would do, let's do the calculation. It's 1 times 1/3, right? Plus 2 times 1/3, as we learned, plus 3 times 1/3. It's the value of the variable times its probability. So what is this? Well, actually, you can see that you have a term that is repeating itself. It's the 1/3 term. So 1/3, if you isolate 1/3, 1/3 needs to, so I'm just kind of isolating 1/3, and then making the distributive property. So 1/3 would have to multiply 1 first, then 2, then 3, okay? So in the end of the day, what you're doing is exactly the average. It's exactly the average. It's the same thing, okay? So the expected value in this case is equal to the average that we learned in high school. Okay, so this was case number 1. I had to pause a little bit the video. Number 2. Now we're going to do an example number 2. So our random variable have now not the same probabilities. It's not equiprobable. So let's say this is 5/10, 3/10, and 2/10. Okay? So being this is a half, 3/10, and 1/5. Okay? So if you think about, and this can happen, right? This is not an equiprobable sample space. So if you think about this X here being a bucket where you have balls 1, 2, and 3, you can think about doing this experiment, and the chances are all the same because the balls have the same size and the same weight. Now we could bias this system, right? We could come and bias this, and we could just we could come here and say, well, ball number 1 is bigger, okay, because it's a half of the time. Ball number 2 is number 3 is really tiny, and ball number 2 is in the middle. Okay, so what's more probable? More probable to take 1, then 2, then 3, then 3. Sorry, 1, then 3, then 2. Okay. So, if I apply the expected value here, this will be, again, the value times its probability, plus the value times its probability, plus the value times its probability. So this row, the first row, second row, third row, you will see that this will be equal to, well, 5 times 6/10. 5 plus 6, that's 11. Plus 6, that's 17, right? Let me just check if I'm doing it right. So this is 6. Plus 6 is 12. So this is, the expected value is 17/10. And it has nothing to do, so this result here is 2. This result here is 1.7. They are not the same. Why? Because they're not the same, and in this case, you don't have the same term to put it in isolation. So 5/10, 3/10, and 2/10, they are different numbers. I cannot put as here, that I had 1/3, 1/3, 1/3, and then I put the 1/3 in isolation, that doesn't happen. So what makes my expected value be equal to my average in high school, or to my mean in high school, is that I have to have the same probabilities here. And these probabilities will represent the number of things, right? So it's dividing by the number of things, because this is an equiprobable sample space. This will allow me to be equal, to do the same thing as the high school average. While here I don't have these numbers and I cannot do that. Okay? So the average that or the mean or average that we learned in school, in high school, is you can only sum up and divide by 3 if the things that you're talking about are equally probable to happen. Okay? If they're not equally probable to happen, then you cannot do this. If you do 1 + 2 + 3 divided by 3 in the second example, you are actually saying that the PDF is 1/3, 1/3, 1/3, and that's not true. Okay? All right, cool. So let's talk now about another statistic. Okay? And the statistic that I want to talk about is actually two different statistics. Okay? And these two different statistics are variance is one and standard deviation is the other. Okay? So again, this statistic is a measure, is a score that you can calculate. Okay? So variance we usually denote as V, capital V of the random variable x. And the standard deviation we denote with this sigma. Let me do it a little bit better here. So it's this sigma of the standard deviation. Okay? So okay, just to wrap up the mean, I want to tell you that you can also use a symbol for the expected value called mu. Okay? So it's what we call the mu notation. So you actually don't say, you can say like, oh, the expected value of this is 10, for example, or you can say the mu is 10. Okay? The expected value of a particular random variable, you can also use the mu notation. Okay? All right, so now let's start and see other statistics. Well, one of them is variance. We denoted it by capital V of x, and the other one is standard deviation. We denote it by sigma. It's this Greek letter here of x. Okay? And as with the mean, I will teach you how to calculate this stuff, and then we will try to understand what it means. Okay? So how to calculate variance? Well, so there are two ways to calculate variance, okay? First of all, this formula number 1, both formulas will result in the same thing, okay? So this formula here, formula number 1 or formula number 2.